So welcome everyone to our third lecture on matrix models. So in total there will be 4 lectures. Today we will see how to solve some matrix models in the large n limit, to which we laid the foundations for the previous time. So the previous time we wrote down how to reduce the original integral over matrices, so of the kind integral dm e to the minus n v of n. So where v is some potential. So how to reduce this to eigenvalue? By doing the integral. So this is the space of Hermitian matrices. So we reduce this to the integral over unitary matrices and the integral over diagonal matrices. So and in the end, the integral, so this integral over unitary matrices can be taken, and then we are left with the integral over eigenvalues, and we wrote down the saddle point equations for this integral, which determine the result. So I will slightly change notation to make it more standard. So previously we had G string, so we just set it to 1 over n as is standard. And this V of m, so normally it will start with some Gaussian term. So trace, by the way, V of m, better to say. Trace V of m. So will be like 1/2 m squared, so which will ensure with this minus sign that the thing is, that everything is decaying at infinity. So, and then, so plus some terms, so for example, maybe some plus g over 4, m to the 4, and so on, maybe a cubic term, so it will be a polynomial potential. So what we found last time is how the saddle point equations look like. When n is large. So in this integral or in the integral over eigenvalues, so this exponent is suppressed by n. So the integral, the leading contribution to the integral comes from the point where this thing in the exponent, it has 0 derivative, and the equations for that were the following. So if the diagonal, so the eigenvalues of our matrix are lambda 1 to lambda n, so then the equations have this form: v prime of lambda I equals 2 over m sum j not equal to I up to n 1 over lambda I minus lambda j. So today we will see how to simplify these equations and how to actually solve them for some particular interesting cases. So let me just remind briefly what is the picture. So this thing is the usual like force acting on a particle in a potential, whereas this thing, so force coming from the potential, whereas this thing is gives a force that leads to repulsion between the particles. So we have a picture of something like, say, the potential may look something like this. So, and then the particles will be driven by this force to, so our lambda i's are some particles on the real line or more generally on the complex plane. So in principle, we will not discuss the complex case here, but potentially they might be on the complex plane. So they will be driven by this force coming from the potential to sit in the bottom of the potential well, something like here. So these are potential, like possible solutions for lambda i's. But then they cannot all sit at the same place because of this repulsion force. We discussed last time that the signs are such that this repels the eigenvalues from each other. So they will fill some regions roughly around the minima of the potential. So like here, so lambda on the lambda line. So what will happen is that they will be concentrated when n becomes very large. So there will be a lot of them filling densely some region on with certain endpoints. And typically, the situation is that we have a finite number of regions whose so with the endpoints being of order O of 1. So n is large, the number of eigenvalues is large, and they fill densely some regions which remain finite. So this one can easily see numerically by solving these equations for some cases. And well, we will build solutions with these properties, and we will see that they actually satisfy the equation. So that's how one can check that it is true. Although to prove it rigorously is in principle quite non-trivial, we will not do that, of course. So the general picture is like this. So there could be many of these cuts, well, the regions where the eigenvalues remain. So the more of them, the higher the complexity of the solution. So we will consider some particular cases today. So any questions on this setup before we actually start with some calculation? Okay, so our goal will be to learn how to solve these equations. Yeah? Yes. Yeah, this is exactly true in the n to infinity limit. That's what we are speaking about. So, yeah. Yeah, well, for example, if the potential is not growing at infinity, but say it goes something like this, so then, of course, even the initial integral will not be well defined. Yeah. But it's not what? Yeah, but in this case, again, the integral would not be well defined, possibly. Yeah, so this logarithmic case is kind of borderline. So that could be more complicated. So let's stick for now. So the idea is let's build our intuition with the simple polynomial potential that is growing at infinity. So that's the first picture to keep in mind. Then in principle, one can consider more complicated stories. Like sometimes you could have a potential which decays, but the eigenvalues are still concentrated somewhere, and so on. But this all is like next level of complexity. Any more questions? Okay, so for the JT gravity, for example, this potential is non-polynomial, has some particular shape, which makes this thing not completely well defined, but still all these methods work nicely. Okay, so so again, a slight change of notation compared from the previous lecture for more standard notation. So we introduced the density rho of x, which is 1 over n, sum of delta functions x minus lambda I. So this means that, so this density, if we integrate it from along some region, it counts how many eigenvalues are in this region divided by n. So rho of x is 1 over n, integral from a to b. Rho of x is 1 over n, number of lambdas in the segment from a to b, or divided by the length of this region. Divided by the length, wait. No, it's just, no, not divided by the length, it's just the number of lambdas divided by n. Well, so the density itself is kind of number of lambdas divided by the length of the region. So you can say, okay, rho of x 1 over n number of lambdas in small region in delta x divided by delta x. So we put this 1 over n here, so that this quantity is of order 1. So there are n delta functions here, but 1 over n kind of compensates that. So in other words, this rho of x for large n is going to be a smooth function with the property that the integral of it is equal to 1 due to this definition. So the total number of eigenvalues is n, but cancelled by this denominator. So the integral will go over the regions where the eigenvalues are sitting. So it will have some, well, finite support, you can say. So it will only be non-zero in some fixed regions of the lambda line, where the eigenvalues are concentrated. So this density is an important concept that comes up a lot when trying to solve equations like that. So this is our definition of it. And the next important object, so here in principle, this can be defined even at finite n, like this. And but it's useful to keep in mind the picture when they condense and fill densely some region. So and then the second important object is the resolvent W of x, which is, well, one can write it like this, 1 over n sum 1 over x minus lambda I, which is equivalently the integral dx rho of x divided by d lambda rho of lambda divided by x minus lambda. Well, since rho is this combination of delta functions, so this thing is a nicer quantity than rho. Okay, rho is kind of concentrated only on some cuts on the plane or on the line, and so it's a bit mysterious. But this thing, so you can see it has for x to infinity, it has 1 over x asymptotics, because, okay, so this integral is perfectly defined if x is away from these regions. If x is somewhere else in the complex plane, then it's a completely analytic function. So which at large x, so this will be 1 over x times the integral. And actually, it could be that the sign is wrong. 1 second, let me double check. I put the most standard definition. I'm a bit worried about the sign. Probably it should be opposite sign. No, it's all good. Yeah, so at the large x, we just forget about this minus lambda. So it will be equal to the integral d lambda rho of lambda, which we discussed as 1. So it's normalized to be 1 over x, where this coefficient is sharply 1. Okay, right, like that. So it's an function which is analytic on the complex plane except for these regions. So which will manifest themselves as cuts here. So cuts as in branch cuts, similar to square root. So when why is that? So this kind of integrals have the property that if we look at the function slightly above the cut, so on the cut this function has a jump. If we evaluate it slightly above this like segment where rho lives, x plus I epsilon minus slightly below. So we have in mind the picture of a complex plane with these segment somewhere on the real line, for example. And then we are evaluating this integral. So the integral goes over the segment. So it is continuous outside of them, but slightly above and slightly below. We compare the values. So one can show that they will differ. The jump will be just proportional to this density. And the precise formula is this 2 pi I actually minus 2 pi I, so minus 2 pi I rho of x. So this formula can be checked like in many different ways. So for example, you can take this just one segment and integrate some constant. So then the integral can be taken. It will be equal to logarithm. And the discontinuity of a logarithm, so in this case on the negative line. So the discontinuity of a logarithm is constant. It's 2 pi I. So you can approximate this integral near any point by assuming that rho is approximately constant there. Then the integral can be taken. It will be a logarithm. The jump of a logarithm is 2 pi I, well, times the value of this constant. So that's how you can derive this formula. And, well, it is valid generally. So so the discontinuity of such an integral is proportional to the density, which is, quite natural property. So now, so that's how they relate to each other. So now our goal is to rewrite this equation in terms of objects which are well defined in the continuum limit, like this density and this resolving. Let's call that resolving. So far, okay, we have in mind the larger picture, but actually the equations are true even at finite time. So to rewrite this saddle point equation, one uses a standard trick. So you see what we have here are objects like 1 over x minus lambda. For example, whereas in the equation, we have objects like lambda minus lambda. So how to get from one to the other? The idea is that to use some kind of partial fractions thing. So for example, if we consider 1 over x minus lambda I, 1 over x minus lambda j, which is roughly the structure coming from w squared. So then this we can write by separating the poles as it's a difference of two poles, x minus lambda I minus x minus lambda j times 1 over lambda I minus lambda j. So, and that is the structure that we like, because that's what we have in our equation. Okay, so that's the idea. So now in practice, what we do is the following trick. So let's consider the combination w squared plus 1 over n w prime. Let's write it out. So w squared, so first of all, w is of order, has this 1 over n. So, and this one, so w squared will have 1 over n squared. And here also, because of this, there will be 1 over n squared. So let's take it outside of the bracket. So, and it will be a difference of two sums. So the first one will be, so w squared just gives a double sum of this thing. The sum over I and j from 1 to n. 1 over x minus lambda I, 1 over x minus lambda j. Now w prime, so when we differentiate this, we get minus, and this thing will become squared. So let's write this minus sum I equals 1 to n, 1 over x minus lambda I squared. So now we can see that in this sum there are terms with I equal to j and I not equal to j. And the terms with I equal to j will be exactly cancelled by this guy. Because so this will be just x minus lambda I squared, which is exactly what we have here. So what will remain is 1 over n squared sum. So it's a double sum, I and j going from 1 to n, with I not equal to j. 1 over x minus lambda I, x minus lambda j. So the whole point of this trick was to get this expression. And this expression we just discussed can be written like that with the fraction that we have in our equation. So we know, so now we plug in this here. So what we get is, so here one should be a bit careful with signs. Let me see. Yeah. So we do one more trick. So let's just plug this in. So 1 over n squared sum. So it's a double sum, I, j, I not equal to j. 1 over x minus lambda I minus 1 over x minus lambda j. 1 over lambda I minus lambda j. So now, since we are summing over I and j, let's do the following manipulation in our head. So consider the second term here. For the second term, let's rename the summation indices I to j and j to I. So then this this thing will change sign, which we can absorb into this sign. And the result will be just equal to the first term. So we will have this 1 over lambda j minus lambda I, and here x minus lambda I. And flipping the sign, it will compensate this sign. So it will be 1 over n squared. So now it will be 2 over n squared sum, okay, this I not equal to j, 1 over x minus lambda I minus lambda j. Okay, and now the second sum, so this first sum does not depend on j, so this second sum runs over j, only this term contains j, and that's exactly the sum that we have in our saddle point equation. So we can plug it in, so we know this sum is just given by derivative of the potential. So hopefully it will fit here. Yeah. Yeah, so we have exactly 2 over n squared. Well, here we have 2 over n. So 1 over n will remain. And we get sum I equals 1 to n v prime of lambda I over x minus lambda I. Okay, any questions so far? So we use this trick with rewriting double poles as a simple pole and this difference of lambdas. So the difference of lambdas, we know this sum from the equation, saddle point equation. So now we reduce this combination of resolvents into this sum v prime over x minus lambda. So now the final step is to introduce the quantity p of x which is 1 over n sum over I v prime of x minus v prime of lambda I over x minus lambda I. So it's the same as we have here, but also we added v prime of x. So now we can write this equation in, so this right-hand side in terms of that p of x. So we have w squared plus 1 over nw prime. So equals, well, what we have here, so let me just write the result. So v prime w minus p. So why? Well, okay, so if we just write minus p, then so this part will give v prime over x minus lambda, like what we had. But we also need to cancel this. So the sum like this v prime over x minus lambda, well, it's just v prime can be taken out of the sum. It will be just v prime times our original result. So this equation is the main tool we're going to be using. So you see it is written now in terms of objects that have a nice continuum limit. So this resolving, okay, v prime is just a function. It doesn't have any integrals or stuff inside it. What remains to demystify a bit is this p. So p is this quantity, but let's look at it more closely. So we assume v is a polynomial. Now what can we say about this function? So at first glance, it may look like it has poles at x equal lambda I. But in fact, the numerator has zeros at the same location. If x is equal to 1 of the lambdas, the numerator vanishes. So in fact, there is no pole. It means that it's a function without any singularities. And well, at large x, it has polynomial asymptotics coming from this v prime. So that means that p of x is just a polynomial. Well, and its degree can be deduced from here. So at large x, so let's say v is a polynomial of degree d, then v prime has degree d minus 1, and here it's divided by x. So it's a polynomial of degree d minus 2 from looking at the large x asymptotic. What exactly is this polynomial? We don't really know. It will depend, of course, on the distribution of lambdas. It's not just read off from the potential. But we know that it just contains a finite number of coefficients, unlike this resolvent, which is an integral, which is complicated. This polynomial just contains a d minus 2 plus 1 unknown numbers in it. And that will be a huge help when we solve this equation for some cases. Well, then finally, the last step is that we say at large n, so that equation is valid for any n. And then at large n, we see that we discussed that w is of order 1. This polynomial is also of order 1. It's 1 over n times sum of n terms. So in this equation, the one term, this one, is smaller than all the rest. So this term, we can remove it at large n. And so at large n, we are left with this equation, w squared equals v prime w minus p. So in which, okay, we know v, we don't know p because it's but we know that it's just a polynomial of given degree, and we have to find w such that this equation is satisfied. So that's the kind of problem we will be solving for the rest of the lecture and analyzing how the solution looks like, and we can build some nice solution. So any questions so far? Okay, so all these tricks, they end up in bringing us to this equation. So let's see how to solve it in the simplest possible case. So the first example will be the free model, the Gaussian case, where the potential is just quadratic. Let me just find the notes for that. Ah, yes. So in general, Gaussian or not, right, so for this case, that means we take v of x, we can just take 1/2 x squared. So all the normalizations like this G string, so we removed it. Well, if you want, you can add some normalization here, like times some parameter. This will just will not change anything, really. So I will take the potential like this. So then how can we solve this equation? Well, first of all, from the equation, we immediately see that this is just a quadratic equation on W. So we can solve it and write it, the solution like W equals, so so there will be 1/2, let's write 1/2. So v prime minus square root, or plus or minus, in principle, square root of the discriminant. So the discriminant is this squared. So this will be there, minus 4p. So we could choose, why do we choose this sign? So the reason is the following. We want W at large x to have asymptotics 1 over x, so decaying asymptotic. And indeed, that will be the case if we have a minus sign here, because v prime, remember, is a polynomial. So at first glance, this function also, well, it contains a polynomial inside it. How could it decay at infinity? But this square root will contains v prime square. So it has a chance to cancel v prime from here. So to cancel the polynomial part and only leave some decaying term. So we choose this minus sign for that reason. And this is our W. But okay, of course, it's not actually the answer because we don't know what is P. So P has to be determined separately in each case. But so for this case, we discussed that P is a polynomial of degree D minus 2. So in this case, D equals 2, which means that P is a constant. So how to fix so now we completely know our solution. So we can write this more explicitly. As v prime is just x, so 1/2 x minus square root of x squared minus 4 times constant. This, I remind, is our w of x. So let's look at it for a second. So what can we say about it? So, well, at large x, this x will be cancelled by this x coming from here, so the function will decay. And actually, while expanding this function, what can we say? At large x, so this, we get 1/2 x minus, so let's take x outside, x square root 1 minus 4c over x squared. So when I expand, so now I expand the square root of 1 minus something small, so this coefficient will be halved. So I get, and so x will cancel, and get 1/2 2c over x, well, plus corrections, that I don't care for the moment. So they are that's equal to c over x. But remember, we discussed that the resolvent has to have asymptotics sharply 1 over x, because this 1 is the normalization of the density, the integral of the density, the total number of our roots lambda. And here we got c over x, so that means c is equal to 1. So you see, yes. Large and negative x will work the same, because here this, well, it will be like absolute value of x everywhere, more or less. But it has to, so this square root, wait, let's see. So, wait, it's a bit weird. So probably I wrote this square root in the slightly wrong way, so wait. Well, yeah, no, at large x it will work exactly the same. So the convention here for this square root is that, so you see, let's say x is large and negative, okay? But then we should choose the branch of this square root, that square root of x squared is approximately equal to x itself. So that's always possible to do. So that's a great question. That's an important point. But you see, so like at high school, we normally would say, okay, that's the absolute value of x. But actually, it's natural to choose it like this. So we have, let me erase something. So better would be to write this square root like, so let's agree, c is equal to 1, so square root of x squared minus 4. Actually, to write it like square root of x minus 2, square root of x plus 2. So what I mean by this is I have on the complex plane of x, I have this square root which has 2 branch points at 2 and minus 2. So after this, I am free to choose how to choose cuts on the complex plane. When so I have 2 branch points, I need to cut the complex plane in some way to make sure the result is a single valued function. But I have the freedom of how to choose this cut. And what I want to do here is to, for example, I could send the cuts off to infinity, like going from here to minus infinity, from here to plus. But instead, I want to choose the cut that connects the 2 points. This is minus 2 and 2. Well, and one way to write it, if the square root is defined with a cut on the negative axis, so that square root is like not defined for negative real values, then one way to write the result is this. And then if you want to evaluate it for large negative x, okay, this will give like I square root of absolute value of x This will give I square root of absolute value of x. So it will be equal minus absolute value of x. In other words, to x itself for large negative x. You see, it's kind of natural. If you look at this function from far away in x, then these two branch points, they kind of collide, and this cut becomes sort of invisible. So the function is approximately equal to literally x everywhere on the complex plane for large x. So that's what we mean by this square root here. Well, in this, and I mean, so in mathematical, like this, you can write it, for instance, in this form. So what do we, any more questions here? Yeah. Well, that's another way to phrase essentially the same thing, because when I write the square root here, I need to also specify what exactly I mean by the square root. So I need to define what branch of the square root I'm using for all values of the thing under it. And that's how I do it here. But yes, indeed, we are kind of using the freedom to choose this branch of the square root in whatever way we like, because it was originated from the quadratic equation. So in this sense, it's really important, this kind of question, because they really define what your function is. So here what we see, if we define the square root in this way, so what properties do we have? So we see that indeed it has a branch cut between two pretty concrete points on the plane, so like I discussed here. So this function, so where was it? Yeah, this function. So this is our resultant. So it's x minus square root. And okay, now it's pretty obvious that if I'm slightly above the square root and slightly below, the square root will change sign. And so this function will have a jump equal to square root itself plus, well, multiplied by some constant like 1/2 or something. So the jump of this function will be the square root. So that means the density is equal to the square root as well as the, well, original result. So because the jump of the resultant is the density. So, well, if you reinstate all of the coefficients and signs, so then you can, let's say it's an exercise, simple one, to check that the density here is 1/2 pi square root of 4 minus x squared. So notice here, I am writing it not as x squared minus 4 like I did there, but as 4 minus x squared. So that highlights the fact that the density is real when x is on the cut. Whereas my resolvent, I want to be real at infinity, where at infinity it is a well-defined integral, should have 1/x asymptotics and so on. The density is naturally defined on the cut, because that's where the eigenvalues have condensed to. And indeed, when I write like this, then right, let's say x equal to 0, it will, under the square root, it will be some positive number. So it makes a perfect sense. Yes. Yes. Yeah, like here. Sorry, could you just say again? If we, yeah, yeah. No, not really. So it's 1/n times the sum of n things. So you can write this, now that we know everything, you can actually write this as an integral with the density. Any sums over eigenvalues, you can rewrite as integrals with the density. Well, and then it's just an integral of rho of lambda with something like v prime of lambda over x minus lambda. It will be just a finite quantity. So it will, well, times n, if you write it in this way, because a sum over eigenvalues will be n times integral with them. You see? So here you can just check it explicitly, but the general argument is that this is a sum of n terms. Each term is of order 1, so it's of order n, and that's killed by the prefix. Okay? Right, yeah, so now we know this density explicitly, so it's defined from -2 to 2. Well, and if we plot it, so what is this square root? So let me remove some things from here. So by the way, this equation that I just removed, the saddle point equation, is also known as the Coulomb gas equation. Coulomb gas, just so that you're familiar with the language. Because it describes some particles sitting in a potential with a repulsive force that's actually equal to the electrostatic force in 2 dimensions. So that's particles with electrostatic Coulomb interaction. It's just, okay, just a fancy name for this equation that we had. Right, so the density, let's plot the density. What is its actually shape? Well, it doesn't, it's not too complicated, square root. So this square root is part of a circle, right? Because density squared plus x squared is a constant number. So it will look like this. Just a circle from -2 to 2. So this is the region where the eigenvalues sit. Okay, and the density, so they are not uniformly distributed. Like in the center of the region, the eigenvalues are packed more tightly than they are at the endpoints. So it's typical, of course, at the endpoints of the distribution, the density vanishes. And in this case, it's just a semicircle. We can check again if we want that its integral is normalized to be 1, like it was written somewhere here. So the density is the sum of delta functions divided by n. So its integral should be 1. That again confirms this coefficient 4. So and it's a semicircle. So that's is known as the famous Wigner's law. So that answers the question, how are the eigenvalues of a random matrix with just Gaussian weight, how are the eigenvalues distributed? So the answer is that the probability density is a circle. And that was quite a famous discovery, and in some sense, this is the analog of the Gaussian law for, of the Gaussian distribution for usual random variables. For example, I think one can prove a kind of central limit theorem that under some like general conditions, eigenvalues of random matrices will be given by this kind of law. You have like large matrices like we have here. Well, of course, not always, but like in reality, also not all distributions of random variables are Gaussian, but it kind of plays the same central role in random matrix theory. So anyhow, it's a basic example, and Wigner historically found it from arguments trying to find the spectrum of some atomic nuclei. And basically the idea there was, okay, we don't know the Hamiltonian, but the Hamiltonian probably is some huge Hermitian matrix. So let's assume it's sort of a random matrix and see what we get from there. And that's this led to these kind of arguments and the semicircle distribution of the eigenvalue. Any questions here? So in principle, that's already quite a non-trivial result. From the original integral over matrices, it was not clear at all how the eigenvalues would be distributed. So, and finally, just before we go for the break, we can also, so using this distribution, we can now compute lots of quantities, like, for example, expectation value of trace m squared would be roughly this just integral dx rho of x squared. If you know the distribution of eigenvalues, you can now compute lots of correlators or trace m to the n, and they can be computed explicitly. So actually, even at finite n in this model, they can be computed explicitly. So this equation, or the saddle point, can actually be solved exactly in terms of Hermite polynomials. And like one can even write something like the generating function for all these correlators of trace m to the n, which will be something like Laguerre polynomials or something like that. So in the n to infinity, it will become a Bessel function. So anyhow, now the important thing in these models is to find the resolvent and the density. When you have them, then you can compute lots of observables just by integrating. Any questions here? Okay, let's, yes? Yeah. Yes, yeah, then that's a whole separate like branch of science that we will not go into. But yes, you can, so this is the leading solution. Then you should look at the equation with this term as well. You do perturbation theory. Yeah, you will get some kind of corrections to all this and so. Yeah, sort of. Well, what will happen is kind of you have a cut, but then you also have some poles separately to this, which will be, so like you have this cut, but then you add one more pole. It's something, this kind of logic is usually used. And that reminds me, so just final comment. So this density, you see, it was originally a sum of poles. So if n is finite, it's a function with poles at locations of lambda. But in the continuum limit, it becomes an integral of some density divided by this x minus lambda. Well, and naturally one can look at the integral, again, as a sum of infinitely many poles. But the point I want to make is that sum of infinitely many poles is a branch cut, in fact. So that's, if you sum a lot of poles that are densely packed on an interval, and then instead of poles, they give you a branch cut, like in this square root. It's conceptually quite a nice point. Okay, let's have a break now and continue later. Okay, let's continue. So we solved the simplest example, the Gaussian matrix model. So we found this semicircle density. So now let's solve a more complicated model with the quartic potential now. It's another famous model that was studied quite a lot. And it's still relatively simple here. So basically, the level of complexity is determined by the potential for the following reason. So here we have this square root, which is always, the solution always has this form. So square root of derivative of potential minus some polynomial. So we have some kind of polynomial under this square root. And depending on the degree of the polynomial, so it will have some roots. And the roots will be connected by those branch cuts. And because the square root has branch points at the zeros of this polynomial, so the zeros will be connected by some branch cut. And then the level of complexity is basically determined by the number of these zeros. So we were in the simplest case with only one cut. So that meant that our function was defined on the Riemann surface, which is a sphere. So the function, just square root, corresponds to the Riemann surface, which is a sphere, two sheets corresponding to plus and minus sign connected by this one cut. But then in more general cases, there could be several cuts, and then the integrals that appear may not really be computable in a nice way. So if we have, so for example, if we want to evaluate some observable, like trace m squared, like I said, that would be integral dx rho of x squared. So in our case, okay, rho of x was just square root, so such an integral can be found in closed form. So then if there were two branch cuts, so then the, so this would be this density, so these kind of integrals would be elliptic functions. And then if we have even more branch cuts, then that would be even more complicated. So that's why typically it's not really possible to consider more than 2 cuts. Well, like sometimes it is. But that's so just to say that the degree of this polynomial determines the complexity because it corresponds to number of cuts. Right, so let's consider the famous problem with the quartic potential, where we take V of Z equal, well, V of X equal 1/2 X squared plus G over 4 X to the 4th. So this, in terms of Feynman graphs, now this is a model that has some Feynman graphs. So these are graphs with sphere topology at large N. Sphere topology and quartic vertices. So the partition function is equal to the sum over them of G, basically G to the power of number of vertices times the number of such, well, sum over all such graphs. So the fixed power of G, the coefficient in front of the fixed power of G counts the number of such graphs that have a given number of vertices. So like if you want to find out how many graphs there are with sphere topology and only quartic vertices that have, say, 20 vertices. So then you compute this matrix integral, the coefficient in front of G to that power will be the number of such graphs. So it's a pretty non-trivial combinatorical problem, which can be expressed as an integral and can be solved exactly. So in fact, it was solved exactly by combinatoric way, and it can also be deduced from the kind of arguments we have here. So I did not really discuss how to compute the partition function, but one can more or less extract it from computing correlators of this kind by using a couple more relatively simple technical tricks. So that we're not going to really discuss here. But let's see how far we can get without going into too much technical detail. So now we want to solve our problem for this potential. So what can we say about our W? So the potential, in principle, depending on the sign of this G, it might look something like this. So now in principle, might have 2 wells. So in such situations, the density itself could be supported on several cuts. But let's look at the simplest possible situation when there is only 1 cut. So basically, we're looking at just a quadratic potential corrected by a quartic. So we restrict ourselves to the situation with 1 cut solution. In principle, if you are unsure how many cuts your solution has, then what you should do is you should evaluate the free energy at each of the cuts, well, or the partition function, on each of the solutions, and compare the values of this free energy, and the one which is the biggest will actually be the dominant saddle point. But that's, okay, that will bring us far away. So let's see what happens under the assumption that we have a 1 cut solution. So we need to solve this equation where V is given by that. So what can we say? So we see W has this form. So where P will, in this case, have degree 2. So since the potential itself is even, this resolvent is going to be an odd function. So like here, the potential was x squared. The resolvent had this branch cut. It was x plus square root. So here, W will be an odd function. So we know that it has 1 over x asymptotics. It has one cut and no other singularity. Well, since it has no it has no other singularities and only one cut, then the only way that it can look is W of Z is. So from here we know that it's, so looking at this thing, so it is polynomial plus square root of polynomial. So this V prime, well, W of X, that will be 1 over Z, 1 over 1 half. So X plus G X cubed. So then we have a square root of some polynomial, but in fact it should be only should only have one cut. So let's write this cut explicitly. Square root plus, okay, well, let's write it as minus square root of x squared minus a squared. We don't know the position of the cut. Times some polynomial, which is a leftover of all these higher degree polynomials, to which actually is quite restricted. So the result should be an odd function. This is already odd, the square root, so it can be multiplied only by an even function. But the most general form would be c x squared plus, bx squared plus c. So why this? So it has to be an even polynomial. If we have a higher power like x to the 4, then it's impossible to impose 1 over x asymptotic, because it would not be possible to cancel it by any other term. So we can only have x squared and constant. So x squared can be canceled by this square root, which will give x, and this x cubed. So they all could combine to cancel the leading x cubed, and in principle can ensure the nice asymptotic. So let's start imposing the conditions that we have. So first of all, well, we just expand this function at infinity. Well, this is just a polynomial, so we need to expand that. So at the very leading order, like I already said, the x cubed coefficient will be g from here minus, so this gives x 1 times b. It has to be 0, since the resolvent must decay. So b is just equal to g. Let me, okay, you can keep it here. So that's something we can find without any calculation. Well, to expand to higher orders, now we need to expand it up to order 1 over x and impose that the asymptotics is really 1 over x. So I will not do it like we did here, since we need to go to several higher orders in the Taylor expansion. Well, rather I did it in mathematics. So what we find, and actually I also asked ChatGPT, but ChatGPT expanded it wrongly. So luckily we may still have our jobs for a few more months, but yeah. So yeah, I used the free version, but well, I admit it is powerful. So anyway, yeah, so what we find is the following. So this W is expanded like 1/2, well, 1 over 4. The x power is this a squared g minus 2c plus 2. So we have two parameters, a and c now. And then the 1 over x term is a4g plus 4a squared c over 16x, plus higher order terms that we don't need. So the asymptotics has to be 1 over x. So this term has to be 0, and this term has to be 1 over x. Well, so first that means that yeah, so we can write this C. So from here we can solve for C. C is equal to 1 plus 1/2 a squared g. And now we plug this into that term and impose that, well, C is here. So impose that it's equal to 1. Well, so that gives the equation that, well, you can double check that if you want. So we get a squared 3a squared g plus 4. Yeah. So here I get 4 by 1/2, that's 2. So I get 3a squared g plus 4 over 16 equals 1. So that's a quadratic equation for a squared. G is a parameter of the potential. What we want to know is the parameter A, the location of the branch point. So that gives A squared equals 2 over 3G. And here plus minus square root of 12G plus 1 minus 1. Well, okay, since it's A squared, it has to be positive. So we choose the positive sign, the plus sign. And now we have our solution. So we found everything in terms of the coupling G. So we know the location of the branch point. So, well, the C guy we also read off from here if we want. And so we can find explicitly, again, nicely, the resolvent and the density. For this already interacting model, which is quite nice. So what can we say here? So now then, in principle, the next step would be to compute the actual partition function. So like I said, there are some tricks that allow you to do this. And then you can actually compute the coefficients appearing here and compare them with known combinatoric result and beautifully see that they match. But we will, so without doing that, there is already something quite powerful we can observe here. So before that, are there any questions? Okay, so what we can observe is that this thing has a singularity at g equals minus 1 over 12. So A has the singularity, well, it's a square root, so not a discontinuity or some pole, but it's a point where the derivatives, if you take many enough derivatives, they will have singularity. And so in all observables, like this trace of some power of m or anything else, this, since they are all, they all will be given by integrals of this density, and the density has this parameter which has the singularity. So the singularity will propagate into all of the observables that you can compute. So in all physical quantities, you will see this singularity at this particular value. So what, how can we interpret it? Well, that's the value where the perturbative expansion breaks down. That's the radius of convergence of this perturbative expansion. The location from 0, well, the distance from 0 to the, at 0 it's a non-interacting model, so the distance from 0 to the first singularity would be the radius of convergence, which is finite and which we managed to find here. And this is something that we can easily compare already with the known combinatoric result. So the combinatoric result is the following. Okay, maybe up to some simple prefactors, but so this number of graphs with only quartic vertices, and so n quartic vertices and sphere topology is equal to 2 times 3 to the n to n factorial n plus 2 factorial, n factorial. So that's a result of some pretty complicated combinatoric argument that gives this number of graphs. So let's call that Cn. So our partition function is the sum n greater or equal to 0 Cn g to the n. So if we know explicitly the coefficients, we can find the radius of convergence. So for that, we can estimate the Cn by using the estimate that n factorial is n to the power n. So, okay, pretty crude estimate, but enough here. So Cn, dropping all the constant prefactors that don't matter. So we write 3 to the power n. That this is 2n power 2n. Here n plus 2 power n plus 2. N power n. So here this 2 to the power 2n, that becomes 4 power n. And combining with the 3, we get 12 power n. Then n power 2n. And here, okay, 2 doesn't matter. And keep just n. So for the radius of convergence, just to explain again, so I need to look at the terms with very large n, because any finite sum would obviously be convergent everywhere. So the fact that we have a finite radius of convergence comes from terms from the infinite tail of the series. So to estimate it, we look at the terms with very large n. So here we have n to the power n. Okay, this n squared, I can write it, but it doesn't matter compared to all the rest. And n to the power n. So this cancels. N squared we just disregard. So basically it behaves as 12 to the power n. So this z at large n is going to be sum for 12g to the power n. So this very crude estimate tells us to up to, okay, so this is the leading exponent term. So then there will be some power-like corrections, like n to some power, and so on. But this already tells us what will be the radius of convergence. If we just forget about the other stuff, that is just the sum of geometric series. So the geometric series has radius of convergence 1. So it breaks down when this argument is equal to 1. It's a standard way to estimate the radius of convergence of some series. So the critical value where this happens is 1 over 12. Well, and that's exactly what we found here, up to this stupid sign. So the reason for the sign is actually very simple. So we took the potential here like this, but remember our integral was z equal integral dm e to minus n v of n. So if we start expanding this potential perturbatively, then it will not be g to the power of number of vectors, but it will be minus g, because it's minus n, minus will propagate here, and each graph becomes with minus g to some power. So in other words, in field theory, normally we write the potential as Gaussian term minus the actual potential in the action. The action is like the kinetic energy minus potential energy, whereas here we put plus. So the conclusion is that true value of g is actually minus our g. So this actually predicts the correct critical value 1 over 12. And that's a pretty neat and simple argument to reproduce this pretty non-trivial property of a really complicated combinatoric calculation. So this is a famous result by, I think, a mathematician named Tat, someone quite famous. So any questions here? So now we'll just make a few comments and we finish on that. Right, so what happened here is that we estimated the radius of convergence for counting so very large graphs with certain restrictions. So this with quartic vertices and sphere topology. So example of such a graph is an octahedron, for example. Actually, it's not immediately obvious how to have a sphere topology with quartic vertices, but that's one way to do it. And of course, there are huge numbers of such graphs. So this is already a problem which in some sense is quite similar to quantum gravity. So when you are summing over surfaces with some restrictions on topology and with some weight given by, well, corresponding to some counting thing, and well, and each power of this parameter will come with some number that basically is the entropy, which counts the number of such configurations. So by extending these ideas, people found quite a lot about some critical properties of gravity, which maybe we will discuss next time. But just to mention, so in fact, this, in gravity, what we want to do is sum over surfaces, whereas here we chose some particular way of discretizing the surfaces in terms of these graphs with specifically quartic vertices. So in principle, the actual properties of quantum gravity should not depend on such discretization. So one should look for universal properties of such statistical models, and one can see that in fact this value is not universal. So while it's not too hard to see, as a really hard homework problem, you can try to solve for square for cubic potential. Well, that's obviously can be found in the literature, but there will be some subtleties with this kind of arguments and so on. But it can be done, and you will find a different value of G. I think it's 3 over 256 or some other value. So it's not. So it depends on the details of your discretization. It's not really a very physical gravity quantity, but what is physical is a more subtle thing, which is the subleading correction to this asymptotics of Cn. So we found Cn is 12 to the power n, so that's not universal. But then the correction one can compute from here would be n to the minus 5 over 2. And now this number is actually physically meaningful. And it's known in the literature as string susceptibility. Well, because people were looking at two-dimensional gravity or two-dimensional non-critical strings, which are all kind of similar. So that's the reason for this name. And it can also be computed by a more subtle analysis. So basically, by considering some sense 1 over n correction. So by sending, so we need to send at the same time our size of the matrix to infinity and the G to this critical value. So in this regime, we want to find the, so the behavior of this perturbative series. So that can be done. Maybe I will say something about it next time, but it requires some more advanced technology of solving this equation with more precision. And but it can be computed, and it matches this 5 over 2 from combinatorics, and that was some of the early famous predictions from matrix modeling. Any question? Yeah. Right. So just a couple more comments about. So first, so this equation. So remember, we derived it from the saddle point equation. Let me repeat it here. So v prime of lambda I is 2 over n sum j not equal to I, 1 over lambda I minus lambda j. So in terms of the density, one can actually write this as an integral equation. So it will have the form v prime of lambda equal probably 2 integral rho of x dx, rho of lambda d lambda x minus lambda. So when lambda is on the cut, when x is on the wait, so here should be x. So when x is on the cut. So strictly speaking, I should put here principal value sign. So which I mean can be justified by some arguments pretty similar to what we already did. I will not discuss this in detail. So but this is an integral equation for the density. So what we were solving all this time actually was this equation. Just we solved it with some tricks by simply looking at the analytic structure of the resolvent and saying like what singularities it could have, what asymptotics it can have. We deduced some expressions for it with some polynomials, and then we just fixed the parameter. So in principle, what we were doing is solving this equation, which is a typical thing known as the Riemann-Hilbert problem in mathematics, when you have some function defined on some cut, and you have to satisfy some equation. So that's that, and then finally, so what could be other origins of singularities, like this limit on the radius of convergence that we found. So another typical, so what are the typical sources of that? Well, one is some discontinuity in the parameters, but also when we are finding some explicit solutions, like for our resolvent, we compute some density, but one should actually ensure that the density is positive. So that, in some cases, switching from a regime where it's positive to negative, that could happen by varying parameters, so that will be a source of singularity. Another source could be collision of cuts. For instance, with a double well potential, there could be a situation where eigenvalues are distributed in the two wells, but then as you lower this distance, even if it's still finite, it could happen that the two cuts collide at some point. So there, a one-cut solution becomes a two-cut solution. And that's another source of singularities in various observables. So that's another source of things that lead to finite radius of convergence and singularities in the physically meaningful quantity. And I think for now, that's all. Next time I will discuss some more advanced topics. Have not really decided which ones yet. Maybe something about quantum gravity or integrability or loop equations, or maybe a bit of all of them. Thank you.